It's fine.
Great. Yeah, great. I was trying to attend some session.
Say hello to you, sir.
But I somehow could not connect it in the morning session today. So I think now the session has to start, right?
Yes, sir. Yes, sir. Good day, everyone. Now we will start the technical session 7 on climate change and future climate projections. This session, I would like to request Engineer Dr. Mohammad Mizanur Rahman, Chief Engineer, Coastal Embankment Improvement Project, Bangladesh Water Development Board, to be a chair in this session. And Wing Commander Muhammad Sultan Masum, retired, Bangladesh Air Force, as an co-chair in this session. I'd like to request Honorable Chair and co-chair to start and conduct the session. Before starting the session, I would like to request session chair and co-chair to evaluate all presenters according to the prescribed format and send us as soon as possible. Thank you all.
Well, good afternoon.
Good afternoon.
Good afternoon to everybody. And I am pleased to be the co-chair of this session. Session is the climate change and future climate projection of
So
the.
now you are chair of this session, sir.
Well, this is co-chair and co-chair, almost all the same thing.
Sir is not available now.
Okay, no problem. I will conduct the session and I will get the help from our co-chair, Mr. Wing Commander, Mr. Name. Please, can you tell me the name again?
MD Sultan Masum.
MD Sultan Masum. Okay, thank you very much. Many thanks to our Professor Tawhida Rashid, Chairman, Department of Meteorology, University of Dhaka, and her team for organizing this conference during this crucial pandemic period and inviting me as chair or co-chair in this session. Actually, I'm now we have
Sorry for the inconvenience.
five papers for presenting in this session. Can you hear me?
Sir, sorry for the interruption. Actually, Dr. L.S. Rathore just arrived. So I would request Dr. L.S. Rathore, former Director General of Meteorology and permanent representative of India with World Meteorological Organization, to chair this session, and Engineer Dr. Mohammad Mizanur Rahman, Chief Engineer, Coastal Embankment Improvement Project, Bangladesh Water Development Board, as a co-chair in this session. So thank you all.
Thank you very much. And I'm so sorry, I just got some connectivity issues, so it was a little late. And welcome to this very important technical session. I think we have 5 presentations in this technical session. And I would urge Engineer Mizanur Rahman to kindly do needful for the proceedings. Dr. Mizanur Rahman.
Okay, thank you. Thank you very much. Actually, our eminent scientist and permanent representative of India with Meteorological Organization, United Nations, Dr. L.S. Rathore, ex-Director General of IMD, is kindly the honorable session chair of this session. So as he mentioned that we have 5 papers for presenting in this session, I would like to request you all participants to keep their presentation within 20 minutes time, which is the allocation for everybody. We have concluded, we will conclude the session at 4:30 p.m. and probably we have 20 minutes for questions and answers. we can, I want to know from my chair that whether we will ask the questions during the immediately after all presentation, or we have to ask questions at the end of the at the end of the session, and that is presentation, all presentations.
It will be good to conclude the session, the presentation with question then and there.
Okay, thank you, sir. So will those who are interested to put their question, they will they will put their question immediately after the presentation, and finally conclusion session will be within 10 minutes. So now, with the permission of chair, I would like to first speaker Professor Dr. David Ferreira for presenting his paper, The Energy Budget of the Tropical Band in Future Climate. Dr. David Ferreira.
Hi, good morning, everybody. Thanks a lot for the invitation. Should I share my screen?
Yes, please.
Can everybody, oops. Can everybody sees my slide?
Yes, we can see.
Thanks a lot. So I would like to first thank the organization for this opportunity to present my work. So this is work I've been doing in collaboration with Roberta D'Agostino, who is working at the Max Planck Institute for Meteorology in Hamburg. And here we are interested in the energy budget of the tropical band in the future climate. So I would like to start by explaining a bit the background of our research. So here you have a schematic of the Hadley cell and energy budget during the northern summer time. So can you see my pointer?
Yes, we can see your pointer.
Thanks a lot. So here we are in the situation where the ITCZ is in the northern hemisphere, and we have a large cross-equatorial cell to the south and a smaller cell to the north. And here you have a schematic showing the distribution of the moistatic energy profile in the atmosphere. So the moistatic energy includes the internal energy, the potential energy, and the latent heat energy. And this is the typical profile we have in the tropics. And here in the blue line, you have the typical profile of just the latent heat component. So in the mean state, what we have is that we have a flow coming in from the south into the ITCZ, which has relatively low moistatic energy and relatively high humidity. There is ascent in the ITCZ, and the flow exits near the tropopoles and goes southward. And this time it has some high moistatic energy and very low humidity. So in the net, this cell is exporting moistatic energy away from the ITCZ, but it's importing moisture into the ITCZ. And if we think in terms of energy budget, what we have is that this export of energy away from the ITCZ must be balanced by a convergence of energy at the top and bottom of the atmosphere. So in the tropics, the net energy input, which is the difference between the top of the atmosphere and the bottom of the atmosphere, is positive. So we have convergence of energy here, and then this is balanced by an export away from the ITCZ. And this is done by converging moisture into the ITCZ and net precipitation. So this is what we have in the mean. And if we can write this in a very simple way, mathematically. So here you have the vertically integrated moist static energy equation, which on average is a balance between the divergence of moist static energy, H, and the net energy input. So again, lateral export is balanced by convergence in the vertical. We can simplify this equation by, and here I'm following the recipe of Neely and Held, by this term is equal to the convergence of flow in the lower part of the atmosphere times the difference in moist static energy between the lower and upper part of the troposphere. So this term is what is called in the literature the gross moist stability. It's a measure of the difference between of the moist static energy stratification. It's always positive, and here it's going to be measured in joule per Kelvin. If we use mass conservation, we can write that the convergence of flow in the lower troposphere is almost equal to the vertical velocity in the middle of the troposphere. So if we write all of these together, we have this very simple equation, which is saying that in the tropics, if we have a net input of energy at the top and bottom of the atmosphere, this is positive, GMS is positive, and so this term is positive, and we have ascent. So where there is net input of energy, we have ascent. And in terms of energy, this means that the net energy input is balanced by export of energy away from the tropics. So now what we are interested in is how this changes in the future climate. So under climate change, we can take our simple equation and take its differential. And what it says is that the relative change in GMS, the stratification in moist static energy, plus the relative change in ascent in the tropical region is balanced by the relative change in net energy input. And there have been already many papers showing that the GMS change is positive. So the stratification gets stronger in future climates. This is mainly because the depth of convection is increasing. I will come back to this in a minute. We also know that the circulation will weaken. There will be less ascent. So these two effects tend to oppose one another when we think about in terms of energy. So a stronger stratification means that there is more export of moist static energy away from the tropics, while a weaker circulation means that there is less export of moist static energy from the tropics. This has been done in the literature previously, and this is showing a plot of the relative change in GMS versus the relative change in circulation. And this is taken from a paper by Chu et al. And what it shows is that the relative change in GMS and circulation are both positive. So here the minus sign is to make it positive. And so you see that to first order, there is a balance between increased export of MSC due to stratification and reduced export of MSC due to weakening of the circulation. So to first order, the balance is going to change in the future like this. But you can also see on that plot that there is not a very good correlation between the change in GMS and the change in circulation. And you can also note that most of the points on this plot are below the 1-1 line. So we think that the biggest problem in this plot is that the change in net energy input has not been included in the balance. And we know that the net energy input has to increase in future climate because there will be a reduced outgoing long wave at the top of the atmosphere. This is what drives climate change. So this is an important term and it should be included in the balance. So the question we are trying to address here is if we can improve the fit in this plot by taking into account the net energy input change. And we also wonder if this way of thinking can apply to different climate than future climate. So to do this, we are going to use CMIP5 climate simulations, and we are going to use three periods. So we have a simulation for the pre-industrial revolution, the PI control. We have simulation for the future climate, and we took the scenario RCP 8.5. So this is a simulation where there is a large increase in greenhouse gas. So the simulation is largely the result, climate change is largely a result of long wave forcing. But we will also consider simulation of the Middleocene. And in this case, there is no forcing by greenhouse gas. There is a forcing due to change in orbital parameter, which means that the forcing is mainly due to shortwave. And we have 9 climate models doing those 3 simulations. So our reference climate is this one. To compute the GMS, I will use the method of Yu and Nilin, which is based on a vertical mode decomposition. And I don't have time to go into the details of that here. Okay, so what do we see? This is showing the vertical velocity profiles in the tropics. So this is average over areas where there is ascent at 650 millibars. And as expected, we see that we have a negative vertical velocity, so it's upward motion. And this is showing the change in the future climate and in the past climate of the Middleocene. So in the future climate, we see that there is a positive change, which means that the circulation is getting weaker. That's exactly what other people have found in the past. For the Middleocene, the change is very small. You can see that the red lines show the model mean and all the models. The change is very weak, maybe tiny bit positive, so a small weakening. And you can also see that the results are quite robust across models, especially at the Middleocene. So the circulation weakens in the future and in the past. So now this is showing the height of the convection. And here you have the height of the convection in the pre-industrial control. We see that obviously the height of convection is the largest in the tropics. So here it's measured in pressure coordinates. So the lower the number, the higher the height of convection. And those 2 plots shows how it changes in the future and in the past. So in the future, we see negative numbers everywhere. So it means that the convection is getting higher. And this explains why the GMS is going to go higher in the future climate. The upper branch of the exit flow is happening at higher altitude, and so it has more potential energy. In the past, there is positive numbers, which means that convection is getting lower, but you will note the difference between the 2 changes. So in the future, the change is of order 100 millibar, but in the past, the change is only 10. So it's a very small change. So now if we look at the GMS and how it changes in the future, this is the GMS for the pre-industrial controlled climate. The GMS is the largest in areas where you have deep convection. And we can see that the Indian Ocean is actually the place where it's almost the largest, with the Western Pacific, the warm pool. In the future, the GMS is increasing significantly by about 10%. I'm going to show you this in a minute. And this is results that we know. So now we are trying to go back to the central question we had at the beginning of the talk is, can we improve our understanding of the energy balance in the climate change? So this is a plot which is like the one I showed you before, taken from Chu et al. Shows a scatter plot for different models of the GMS change versus the change in ascent. The round points here, the circles, show the changes for the future climate. And here the crosses show the changes for the past climate. And this is the 1-1 line. So we can see that as in Chu et al., most of the points are in the positive quadrant. So positive here means that there is a weakening of the circulation, and positive here means that the GMS is getting stronger. This is exactly the result of Chu et al. And we see also that there is not a very good correlation between the points, and most of them are below the 1-1 line. So now if we look at the past climate, we see something a bit different. So the GMS on average is getting negative. So there's a weakening of the stratification in the tropics in the past, but the circulation is also positive. So there is also weakening of the circulation in the past. So in the past, we have the change in circulation and the change in stratification, which work both in the way of exporting less energy from the tropics, while in the future, the two changes tend to oppose one another. So that's one point. So now we're trying, that's the main point of, oh, can we do a better job if we include the change in net energy input into the atmosphere? And so that's what happens if now I'm plotting the change in GMS versus the change in circulation with a correction for the change in net energy input. So if everything was good, all the points would be on the 1-1 line. They are not. But what we see is that in the future climate, we have all the points are getting upward if we include the correction for net energy input. So the points are getting closer to the 1-1 line if we include this correction. Interestingly, also, there is one model which is the opposite of all the other models. So in this model, the net energy input is negative. And so with the correction, we bring this plot downward, this dot goes downward. But even in this case, it gets the dot gets closer to the 1-1 line. So by including this correction, we move the plot closer to the 1-1 line, and we are closer to get a closed budget. We can look at that for the past climate too. So all the dots here were positive here, and the net energy input is in the past was negative. And if we include this correction, then all the dots move closer to the 1-1 line. So this is a measure of how good we understand the energy balance in the future climate. If we don't include any change, the slope is 0.31. But if we include it, the slope gets much higher. It gets to 0.64. So it's not perfect, but there is a very significant improvement in the energy balance if we account for the change in net energy export. So I would like now to summarize our findings. So what we know from the previous literature, and we have found again in our study, is that in future climate, we will see a strengthening of the gross moist stability and a weakening of the circulation. And these two effects tend to oppose one another in the energy budget. The strengthening of the GMS means more export of energy from the tropics. The weakening of the circulation means less export from the tropics. But to first order, these two effects tend to balance. we know that there is also a change in the net energy input into the tropics. So the net energy increases too, and it's important because it's the driver of the climate change. And so the energy balance requires that the GMS effect must be stronger and must dominate the balance to compensate for the net energy input. And so if now we account for the net energy input, we have a much better balance for the future climate, in which in the future, the any input is going to increase, the circulation is going to weaken, but the GMS will also strengthen. And this balance is such that the GMS effect has to be the dominant effect to balance the energy input. And finally, I just want to say that in the past, we saw something very different. So the changes are much smaller at the middle Holocene. We see any decrease, the GMS weakens, but the circulation strengthens. So it's not an opposite change to what we have in the future. But even in this case, if we account for the any change, we have a much better balance of energy. We understand it better. One key conclusion of this is that the Mid-Holocene is not an analog of the future climate change. And I know that in the literature, people have tried to make the Mid-Holocene like a mirror image of what will happen in the future. But as we found in a previous paper led by my co-author, my colleague, Roberta D'Agostino, the past changes are not analog to the future. And this is in part due to the fact that in the past it was a forcing due to shortwave, while in the future it's going to be a forcing due to longwave. And so you can refer to this paper, and we are in the process of writing those results. Thanks a lot for your attention. Oh, sorry. Should I? Are we taking questions now or no? At the end.
Okay. Thank you, Mr. David Ferreira. Actually, I forgot to mention that Dr. David Ferreira, professor from Reading University, UK. Thank you for your nice presentation.
Thank you.
Clear, and everything is clear to everybody. And probably you have tried to mention regarding the change in the circulation in a future warmer climate, stratification of soil energy, moisture, and increase of net energy input in future climate. So if anybody has any question, please floor is open now. Please open your question now. Thank you. Any question?
If there is no question from audience, David, I would like to ask a question, and my question is related to the height of convection in the tropics. You mentioned that the future climates, because of strengthening of GMS, and though there is a weakening of circulation, but the prime driver of change is NEI. And therefore, the maximum height of convection increases in future climates. That's what, if I understood correctly.
Yeah.
And so that leads to, you also mentioned that increase in the potential energy, and under these circumstances, can we contemplate more fearful extreme weather events in tropics?
Oh, this is a good question. I do not know the answer to that. It's in part because the model we have been using are rather coarse resolution. And so they're not very good at capturing extreme events. I understand your point. I think it's a very good point. We should maybe worry about more extreme events. But the model we are using are doing this in a very smooth way. And I think regional climate modeling is probably the way forward to explore this question.
Thank you.
Thank you. Now, I would like to invite our second speaker, Mr. Muhammad Tanjilur Rahman, Department of Meteorology, for presenting his paper, Dynamic Downscaling for Rainfall Projection over Bangladesh using Regional Climate Model 4.7. Mr. Muhammad Tanjilur Rahman.
Assalamu alaikum. Thank you. I want to thank my honorable chair and co-chair for giving me the floor. This is me, Muhammad Tanzilur Rahman, MSc student from Department of Meteorology, University of Dhaka, and now I am presenting my topic on dynamic downscaling for rainfall projection over Bangladesh using Rexium 4.7. This is the total outline of my presentation, and these are some introductory words from me. If I go through the objectives of my works, then the objectives are to examine the model performance by analyzing simulated monthly, seasonal, and annual rainfall over Bangladesh, to validate bias correction, of model simulated rainfall with observation, to provide future rainfall position over Bangladesh. In data used and meteorology, for model simulation, I have used 3 types of data. Then terrain data, SST, and ICBC. In terrain section, it needs elevation data, land cover data, and soil data. And for SST, I have used NOAA YSST data for weekly mean data of 1 degree horizontal resolution. And for in ICBC, that means initial condition and boundary condition. For rainfall climatology analysis, I have used ERA Internet 75 data, that is of 0.75 degree horizontal resolution for the period 1990 to 2018. And for future rainfall projection, I have used ECAM 5 at 1.8 degree resolution for the period 2030 to 2040. Then after simulation, I have compared this data with observed rainfall from 2 sources that are from BMD daily rainfall data accounted from 34 rain gauge stations. And another one is monthly rainfall gridded data, that is from CRU of resolution 0.50. And in model setup, I have downscaled the literal condition data in 25 kilometer horizontal resolution, and then with the cumulus scheme of mixed, that is MIT Emmanuel over land and Grail over ocean. In the next, this is a presentation of representing my domain, and the black box representing the study region, that is Bangladesh, and the right figure representing the stations of BMD 34 stations are representing here. On the next, the total methodology of my work is representing here. After simulation, the rainfall parameter has been extracted, but after excluding the first year as an spin-up period, then obtain monthly, seasonal, and annual at scale of data from the 6-hour output. Then as same observed data has been regridded into 25 kilometer from in case of BMD, the station data has been interpolated into gridded data, and CRU data are regridded into 25 kilometer. In analysis part, I have done in 2 ways, spatial and temporal. In temporal scale, area average rainfall has been analyzed and compared with the observed rainfall from BMD and CRU also. And also in addition, mean bias, root mean square error, and correlation coefficient also calculated to check the differences, to check the get the differences. So in spatial analysis, simulated rainfall has been compared in seasonal and annual scale with BMD and crew data, and percent bias and mean bias has been accounted as for annual rainfall. After that, bias correction have been conducted. The linear scaling method has been employed in this case. Here, the future bias corrected rainfall has been obtained by multiplying the future simulated data with correction factor that is obtained by the ratio of mean observed rainfall with reference mean observed rainfall. Reference mean rainfall. In this case, when I validate this method for the simulated data, I validated for 2016, 2017, and 18, and found quite satisfactory result. That's then I go for future projection. In future projection, simulated future rainfall has been compared to observed rainfall of BMD to get the changes predicted for future under RCP 8.5. Then in this temporal analysis, three figures is representing here about monthly, seasonal, annual. The top right representing the monthly changes, monthly differences between observed rainfall as well as with model simulated rainfall. Here we can see that in June, July, and August, model overestimate in Bangladesh and underestimate in some months like March, April, September, October, November. We can see that more precisely in seasonal scale. In that case, we can see that monsoon season, in the monsoon season, model overestimated more and underestimated in the pre-monsoon and post-monsoon, while winter looks like similar. In annual average rainfall in the left side, we see almost every year's model gives same, almost same, but in some years model overestimates rainfall for annual scale. This is the some calculations of the observed rainfall with observed rainfall and model simulated rainfall to get the changes more precisely. In that case, we can see that correlation coefficient with BMD and with crew, that is 0.52 and 0.63, and root mean square we found 337 for BMD and 320 for crew. For spatial cases in seasonal scale, we see that in pre-monsoon, monsoon, post-monsoon, and winter, in all cases model overestimate in the region of southeast, where closely to the Bay of Bengal, and in the Chittagong region, that is of quite a complex topography, and underestimated in the northwest region, and in some places of northeast region sometimes in monsoon we can see, and some quite fair estimation have been found in the central region of the country. In the analysis of annual mean bias and percent bias with respect to BMD in the right and with crew in the left, we can see that clearly the model overestimate in the southern side, that especially in the southeastern region, and model underestimate in the northeast and northwest border regions. So after that, I go for a bias correction, and in the bias correction represents that when I bias corrected for the year 2016, 17, and 18, the bias corrected and validate for this region. The reference period has been taken for 1991 to 2015, and then we found with the linear scaling method the quite satisfactory result that the model after bias correction it gives quite similar to the observed rainfall. So after that, I go for the future projection, and in future projection, two scale have been used in seasonal and annual. In seasonal scale, pre-monsoon, monsoon, and post-monsoon have been displaying here, and in that case, we see the in case of pre-monsoon on the left one, the figure A, representing the decreasing pattern of rainfall in the northern region, western eastern region, and increasing pattern in the southeastern region near to the Bay of Bengal. And in monsoon season, we found increasing pattern almost all the region of the country under RCP 8.5. In that case, mostly increase in down north southeastern region, as well as some increase in northwest region. And in post monsoon, we can see that decreasing pattern may found almost central regions of the country, but increasing in southeastern region as well as northwestern regions. So in annual scale, in this case, the changes have been found that in overall annual scale, rainfall is increasing and especially specifically increasing in southeastern region, where sometimes some increasing found like 60 to 70 in the northwestern region, and moderate increase in the central region, where in the left figure we can see that the annual projection of rainfall for the 2031-2040, where rainfall may increase in 2034, 2038, and 2040 under RCP 8.5, according to the REXIAM simulation. That's from the result. And if I want to conclude all the results, then I want to say that the study found that the model overestimates in monsoon season remarkably and underestimates in post-monsoon and pre-monsoon. And in its partial distribution, it indicates model generate rainfall is higher in the southeast complex topography and underestimate in northeast and northwest border region, but almost fair in other regions. But in linear scale method, bias correction reduce model bias with satisfactory result. After and in future projection, bias corrected future rainfall generated by the model found high amount of rainfall in annual mean, which is about 73%, and in the decade of 2030 to 2040 under RCP 8.5, and in seasonal scale, rainfall may decrease in pre-monsoon and post-monsoon, where noticeably in the central part of the country and in monsoon, rainfall may increase all over the country, remarkably in the southeast and northwest region under RCP 8.5. That's all from my research work. And finally, I want to acknowledge Central Department of Hydrology and Meteorology, Tribhuvan University, Kirtipur, Kathmandu, Nepal, for the enormous assistance and supervision in REXIAM model simulation and analysis, as well as I want to acknowledge Bangladesh Department of Bangladesh Meteorological Department, BMD, Dhaka, Bangladesh, for providing record rainfall data, as well as tremendous guidance in the study. Thank you all. If you have any query or question, please.
Thank you very much, Muhammad Tanzilur Rahman, for presenting a nice paper and research work for Bangladesh. Actually, you have given the message that almost all the seasonal rainfall will be increasing for the next century, that is 2100. So that is message for us. I am now opening the floor for questions from the audience. If there is any question, please.
Janur Bhai, if there is no question, can I ask one?
Yeah, please, sir.
Definitely.
Thank you, Tanzilur. You made a very nice study, and in some way, your finding corroborates the findings of David also, because he also indicated the increase in convection in tropical region, and to that extent, you corroborate with each other. But interestingly, maybe you would like to examine, because monsoons become very fearful, and the kind of anomaly you presented is 350 around, or that order. And though pre-monsoon and post-monsoon, they are underestimating, but the magnitude is much smaller. And so therefore, when you look at the annual data, the influence of monsoon otherwise also reflect in the precipitation. Now, what is required to be analyzed is that how it links to the circulation pattern. And during monsoon, maybe the southerly flow becomes more pronounced, and so therefore, when it encounters the hills of Chittagong and further to the Khasi Jayantia and the foothills, you get enhanced precipitation. Whereas during pre-monsoon and post-monsoon, the flow is more of meridional. Pre-monsoon, it is primarily westerly and then changing to easterly in post-monsoon. So those circulations might be weakening, and the southerly circulation is increasing. This is a kind of for future study, if you would like to probe it. Thank you very much, Chairman.
Thank you, sir. Thank you.
I have some suggestion, not any question. That is, I am professional. I am water resource engineer, basically. We need this information very much. We are using this information in our profession for the water resource planning. And since you have got the increasing pattern in the monsoon, again you have got some anomaly in the post-monsoon period.
Yes,
also you have got the more rainfall projection in the east, northeastern part of Bangladesh, as well as you are getting decreasing trend in the northwest and western part of Bangladesh. So these are also prevailing some drought portion area, Barind area, also the northwest, the Howrah area, where we are getting flash flood in northwest part. We are getting drought. That is we are providing supplementary irrigation over there. So if you can extend your work, your research to find out your frequency analysis, find out the future design rainfall, that is 100 years return period or 200 years return period, because you have now future rainfall projection. You have past rainfall data. So using both data, you prepare the return period for 100 years or 200 years, 500 years, then compare it, and you can propose to us. We can use this in our professional life. Thank you very much.
Thank you, sir. Thank you, sir. I will do, sir. Thank you, sir. Thank you for your suggestion, sir. Definitely, sir. I will in the future. I will do. I will extend my research work on that case, on this sector.
Thank you.
And also, there is a question in the chat box.
Yeah. Is there any question?
Yeah, there is one question in chat box. Tejulur, you can read this.
Hello, can you hear me? This is Ben Harrison from the Met Office. That was an interesting talk. I was wondering with the rainfall changes, how much is due to like thermodynamics? So did the increase in temperature affecting humidity, and how much is to do with circulation changes from the GCMs that drive the regional model?
Sir, I have a plan to do in the future on these sections on thermodynamics as well as in circulation changes, comparing with this with the study of in the future with my sectors. In the future, I will do. I hope I will find some results on that.
All right.
Thanks
a lot. Cheers.
May I jump in and just quick remark? Is it okay?
Yes, please.
There is a paper that actually by my colleague D'Agostino, who suggests that in the future the changes are driven mainly by thermodynamics, and the circulation change is actually contributing to a reduction in precipitation. But it needs probably refinement because it's been done for the whole Indian region, not just Bangladesh. But I thought it would be a useful remark.
Thank you.
Yeah,
Can I add something?
Yeah,
Can
please.
I add something?
Yes, please, sir.
Yeah. Thank you. Actually, Mr. Tanzilur Rahman is associated with us. So regarding David questions, actually one thing is very important. As it has been projected that rainfall will increase. Of course, for increment of rainfall, sufficient moisture should be there. Without moisture, no rainfall will increase. But in context of Bangladesh, as Dr. Rathod sir already told that, we have two sets of intervention, two sets of process, atmospheric processes. So something is coming from the Bay of Bengal, and in another way, something is coming from the as a western disturbance to our country. And in some cases, we have having the combination of both the circulation system over in Bangladesh. So once it has been indicated that rainfall will be increased in some season, and definitely it would be decreasing in some other season also. As this is the indication, of course, there the circulation system would be there, maybe bay originated, or there would be the that means there would be the what is called high influence from the bay originated flow. Due to that flow, the rainfall will increase. Of course, we have in the northeastern part, there is the Assam and Khasi Hills, and in the southeastern, we have the Chittagong region. Both the hills will play a good role for as an orographic effect. So this circulation system can be tested in future to see, yes, this year the rainfall has been increasing. Okay, whether we have to, whether definitely the circulation system has been contributing to that or not. But of course, as of our climatological aspect, circulation system, number of circulation system as well as enhancement of circulation system would be enhancing, and accordingly rainfall would be the increasing in trend. That is the indication like that. Thank you.
Thank you, Dr. Abdul Manan. Now I will invite our next speaker, Dr. A.R.M. Taufiqul Islam. He is Associate Professor in Department of Disaster Management, Begum Rokhaya University, Rampur. He will present his paper on assessing vegetation change and extreme climate and their mechanism over times in Bangladesh. Dr. Taufiqul Islam, please.
Thank you, Honorable Chair, and respected dear audience on virtual platform. I am A.R.M. Taufiqul Islam, Associate Professor, Department of Disaster Management, Begum Rokhaya University. Can you see the slide?
Yes, we can see you. We can see that slides. No problem.
Thank you. My topic is assessing vegetation change and extreme climate and their mechanism over time in Bangladesh. At first, I want to say why I choose this topic. Temperature and precipitation are regarded to be a vital factor affecting the distribution of vegetation dynamic or vegetation changes. Temperature is now a burning climate change is now a burning issue for sustainable socio-economic development, and in recent year, global climate is continuously warming, and under the climate warming, extreme climate has increased its frequency and intensity, which affect the growth of vegetation change. And so it is the question, the nexus between vegetation and climatic factor has been a topic of interest among the scientific community. And climate extreme have a substantial impact on vegetation. However, little is known the vegetation response to climate extreme in Bangladesh. That's why I choose this topic. Here is some outline on the presentation. The background of the study. We know that Bangladesh is a low-lying riverine country and a typical subtropical monsoon climate. About 80% of the country's annual rainfall occur in the monsoon period, and average temperature 25 or 26, and lowest temperature is 7.2 and in January, and highest is 31 in July. And we know that Bangladesh is one of the most vulnerable country to climate change in the world. Climate vegetation dynamics index, mm, uh, that is the normalized difference vegetation index, are widely used to represent the vegetation coverage of changes on different spatiotemporal scale. There's some problem here. The problem statement. The main climate extreme. Why climate extreme increase due to global warming, and hot day and heavy rainfall or flood or drought, cold damage in some region, and the fragile the grassland ecosystem, and the land desertification, or either land degradation, industrialization, and urbanization. The problem here, here you see the some knowledge gap of the existing literature. Islam and Mamun 2015, variation of NDVI and its association with rainfall and evaporation over Bangladesh. They have found some relation, rainfall rate and total evapotranspiration and vegetation dynamics. And another study, NAT 2014, a quantitative assessment of forest cover change, a part of the Bandarban hill tracts using NDVI techniques. And on the other hand, in the impact of climate change and human activity on surface runoff in the China have found a significant relationship um, with the climate extreme and vegetation change. Human settlements, pattern change, vegetation, and land use contribution of environment and human. The Lee, Liu, and most recent study, Shu et al. 2020. In Bangladesh, the lack of study in the nexus between extreme climate and the vegetation change. Here the research question: what are the changing pattern, trend, and periodicity of NDVI, extreme temperature, precipitation at monthly and seasonal scale in Bangladesh? What are the variation of temperature and precipitation at seasonal scale in Bangladesh? What are the spatial and temporal relationship among the NDVI, extreme temperature, and precipitation in Bangladesh? Here, my two objectives: to explore the relationship between NDVI and extreme climatic index at different temporal scale, and to examine the spatial distribution of degree of correlation, and to determine how NDVI responds to extreme climatic index. In this regard, I get the data, the temperature and precipitation data collect from the BMD, Bangladesh Meteorological Department, and NDVI data obtained from Natural Oceanic Atmospheric Administration, NOAA. And then in this study, I used 20 weather station data for extreme index calculation. Here, the temperature and precipitation index. Mainly, I categorize into two types, like the absolute base index, and another is the percentage base index. Absolute base, there is TX, RX 1 day, RX 5 day, 10 day, and temperature is minimum, monthly minimum value of daily minimum temperature, monthly maximum value of daily maximum temperature. And another is cold night, cold day, warm night, and warm day. And here, I use the linear regression and Pearson correlation coefficient, detailed fluctuation analysis, and wavelet transform model, cross wavelet analysis. Here, some software I use to carry out this analysis. Here, the flowchart and here the flowchart of the study adopted for this research. The NDVI and extreme climatic index to check the quality control in the paired sample t-test. All of those are significant. I found all of the significant. And the first objective, change in annual NDVI and extreme climate index for Bangladesh during my study period is 1986 to 2017. I choose this period because the current period, and according to the IPCC, they said the 30-year decade are the most warming compared to the last last 100 years. Here you can see the NDVI is increasing at a rate of 0.005 day per 10 year. Here the rainfall is decreasing. Extreme rainfall is decreasing, and then maximum temperature, high temperature increase and low temperature decrease. Cold index are decreasing and warm index are increasing. Clearly, this linear regression analysis show that. Here, the Pearson correlation coefficient. We correlate the monthly scale with NDVI and the 9 selected climate index. Most of the cases are as a good correlation are found in May, June, July, and other month is negative, either negative or weak correlation. Here, particularly, we can find the climatic change and vegetation growth from 1986 to 2017 during the only for crop growth period. Here we found a significant correlation in the precipitation index with crop growth, a significant relation. Another in the seasonal scale, NDVI with 9 selected climate index. Here we found the most of the significant correlation NDVI with climatic index is significant correlation in found on the climatic index in the pre-monsoon and monsoon season. But rest of the month, rest of the season like winter and post-monsoon are negative, insignificant relation are found. The annual variation, this figure shows the annual variation of NDVI, average temperature, and precipitation. Here, most of this case high in the NDVI in the July and May, and the similar trend pattern follow the temperature and precipitation. DFA, detailed fluctuation analysis show that the NDVI are increasing. At the same time, warming index are continuously increased, but extreme precipitation index, no change occur. Here, the Weber transform of NDVI and extreme temperature and precipitation. Here we can see the 1986 to 2003 have a significant band. A periodicity was observed in the warm temperature index compared to the cold temperature index, and also a significant relation found in extreme precipitation. Here, the spatial pattern of decadal trend of NDVI. Spatial pattern most we can see that here the northern, northwestern, and southwestern period are high NDVI, and compared to the other region, and the warm temperature index show a spatial heterogeneity. and compared to the cold temperature index. Rainfall also show a similar to the cold temperature index. Here, the special pattern of correlation coefficient between monthly mean NDVI and extreme temperature index. You can see the we have divided according to Banglapedia, we have divided four vegetation types. The number one is cultivated type, number two is the marshy type, number three is the low hill type, and number four in forest forest type, mangrove type. And here in this of this figure, we can see in case of warm temperature index, we can see the marshy type is insensitive compared to the cultivated and low hill types. Here, we use a reanalyzed data, ERA 5, and here we can see the atmospheric circulation, the causal relationship of the mechanism of the extreme event. Here we divided into two parts. The one is 1996 to 2001, and another is 2002 to 2017. On the basis of sequential Mann-Kandel analysis, we have found a significant change point. And here we can see the geopotential height is the enhanced geopotential height, and then no significant anticyclonic pattern, and higher cloud cover, low solar radiation, higher humidity that lead to the climate extreme, change the climate extreme in Bangladesh. And here the main findings and summary. The vegetation in Bangladesh has significantly risen during the last 32 years at a rate of 0.005 day per 10 year or decade. NDVI had a similar trend with warm extreme, where it show a reverse trend with cold extreme and cold precipitation, no, sorry, extreme precipitation and cold index at annual scale. NDVI show a positive relationship with warm temperature index in all seasons except pre-monsoon. While precipitation extreme show a weak negative correlation with NDVI at seasonal scale. Warming at day are higher than the warming at the night. The impact of extreme temperature index show mostly in May and June with the time lag of minimum one month. Whereas the extreme precipitation demonstrated a significant association with time lag, no time lag. In future, extreme climate index will continue to maintain their current trend pattern according to the detailed fluctuation analysis. Large scale circulation analysis that we can found that no visible anticyclonic pattern, enhanced geopotential height, and high monsoon flow, and decline the high cloud cover, inadequate solar radiation, along with high humidity in the Bay of Bengal being transported to northeast direction might have contributed to change the climate extreme in Bangladesh. Here, compared to other study, this study has three novel aspects. First, the nexus between vegetation change and extreme climatic phenomena on various spatiotemporal scale are systematically investigated for the first time in Bangladesh. Second, these studies shed light on current and future impact on the future extreme climatic phenomena on vegetation growth. Third, the probable mechanism of change in extreme climate phenomena has been explored, and the nexus between NDVI and climatic extreme established in this study indicate the increasing warm temperature is in line with the global warming, may have implication for ecology and environment of Bangladesh in future. And future research focus, the impact of temperature and precipitation extreme on agriculture sector, and the link between drought risks or vegetation dynamics, and the correlation between NDVI of different regions with different atmospheric parameters, human activity and impact on vegetation change at the regional scale. Those deserve future investigation. Thanks. Thank you.
Thank you, Dr. Tawfiqul Islam, for presenting an important and significant research paper where you have shown that rises in temperature extremes in the northwest and west region in Bangladesh. Now I would like to request the audience for put the questions to Dr. Tawfiqul Islam. Floor is open now, please. Nobody is there to question him? If there is no question, then I would like to just give a suggestion to Dr. Tawfiqul Islam. Actually, you have given the indication that temperature rise will be there in the north. That is the overall message from your presentation, that temperature rise will be there in the northwest and western region of Bangladesh. So can you make one quantification that temperature rise with the time horizon, that is the temperature rise in 2030, 2050, and 2100, because you know where we have our Bangladesh Delta Plan 2100, where we have given the flexible plan for 100 years. So if you can give that time horizon of your temperature rise, then that plan, it is a 100 years plan, which is not rigid. Actually, that is the flexible plan. Time to time it will be changed. We will revisit the plan. So in that case, your research may be helpful to make the updating of that plan.
Yes, and thank you, sir. I have a plan in the next time. My next study will future projection. And this is the current projection, and next is the future projection with vegetation change and extreme climate.
With timeline, because your this temperature rise, you have mentioned that it will be harmful for the ecology and environment. In that case, in this area, barring area, North Bengal of Bangladesh, that area livelihood may be changed. So that will be a good projection for the future planner. Thank you very much.
Bijanur Bhai, can I chip in?
Sure, sir, please.
Thank you, Tawfiqul. Very good study. And for future plan, I would suggest that assessing the vegetation change primarily based on rainfall or other climatic parameter may not give the holistic picture. You need to also look into two more aspects, which are also directly linked to the changing climates. One is the changes in the radiations. And because radiation, particularly the photosynthetic active radiation, PAR, is very critical component for changes in vegetational aspects. That has a positive impact if it increases, and then the UV and other radiation will have other kind of impact. So the dynamics of this radiation also need to be considered. And so also the projected CO2 concentrations, we have crossed the limit of 400 ppm. And there are future projections of CO2, because CO2 acts as fertilization. So it's a fertilizing agent, and therefore enhance the photosynthetic process. And therefore, the vegetation changes would be positively impacted. So you need to look the things more holistically. So kindly include those aspects in your future plan. Thank you. Over, sir.
Yes, yes, sir. Thank you. I will consider our next study in future plan. Okay. Thank you for your.
Thank you, Dr. Tawfiqul Islam. Now we are going for our next presentation. Dr. Benjamin Harrison, he's scientist from Meteorological Office from Headley Center, UK. So his presentation title is Exploring Use of New Regional Sea Level Projections in the Development of South Asia Coastal Climate Service. Probably his presentation will be very interesting. Mr. Dr. Benjamin Harrison.
Hello, everyone. Thanks for inviting me to the conference. I hope you can all see the screen. Is that up showing?
Yes,
so
we can see. Yeah, we can see you.
That's good to hear. So today I'm going to talk about some new sea level projections that we've generated, that Met Office generated for use in climate services. The method itself is not new, but it hasn't been applied in this region to as many locations. And one of the things about sea level, which is different perhaps from things like rainfall that you've heard about earlier today, is that in some ways things are simpler because the direction of change, at least there's certainty over that. Whereas for rainfall, for example, there's uncertainty about whether you could have a near-term increase or decrease. So that's one of the things that could make sea level projections perhaps slightly easier for long-term planning compared to working with other forms of projections. So there's two parts to the talk. The first part, I'll do a brief kind of intro to the program that is funding this work, and then I'll go into the sea level projections that we've kind of produced for South Asia, and I will focus mostly on Bay of Bengal locations in this talk. So the ARC program is the Asia Regional Resilience to a Changing Climate program. It's funded by the UK government, and it's jointly delivered by the Met Office and the World Bank. It started in 2018, it runs for 4 years, and there are bits of work across all timescales, from like early warning systems through to climate projections, which is what I'm going to be speaking about today. So these new projections are based on methods developed for the UK national projections, and they're in turn based on the process-based projections from the fifth assessment report. It extends that method to local sea level. So for this program, the ARC program, there's 3 components. There's a work package on short-term forecasting, another on seasonal forecasting, and another on future climate change, which is what I'm working on. And I'm leading the coastal component of that work. So the idea is that when we did a review, there wasn't any local scale information on sea level rise that we could find in the literature or that was available from public, open sources. And so we've ran this new set of projections based on work from the UK, which has been published in a paper by my colleague Matt Palmer. And the idea is to develop kind of guidance on future risks from extreme events, and also enhance the kind of capacity of organizations in the use and communication of sea level information. And one of the things we've been doing recently is training workshops on the use of sea level projections, which you can see the flyer for in the bottom left corner, with a collaborator, Professor Saiful Islam from the Bangladesh University of Engineering and Technology. So on to sea level projections. So the first question we were interested in is, how much geographical variation do you see? So if you want to prioritize a certain section of coastline, you might want to know, is one area more vulnerable than others? For example, is there areas where an implementation will work or has to be brought forward? And currently we don't really have the resolution to do that. So this was an exploration of what we can find out. So here are some of the locations we looked at for the Bay of Bengal. So this is for RCP 2.6, and the yellow kind of areas are showing the local projections and the blue the global. So you can see on the whole, there's a slight, I guess the global slides, the slight reduction compared to the global average for sites in this region. But when you go to the south of the Bay of Bengal, Port Blair and the Andaman Islands, you see they're more or less in line with the global. If anything, at the upper end, there's a slight increase, but that's because of the greater uncertainty for the regional projections versus the global because of some processes that I'll come on to in a minute. And this is the same plot for RCP 8.5. So you see the same kind of difference with the local projections being slightly less than the global, but they become closer to the global as you go to the higher forcing scenario. So the next kind of question we were asking is what drives these variations? So these are the processes that contribute to sea level change. This is the sea level jigsaw, my colleague Matt Palmer calls it, and we're focused on this kind of central column. So like the atmosphere in the talk we had earlier, you can have changes in the ocean circulation and density that affects sea level. We also have these things called GRD fingerprints, which is essentially how the Earth's gravitational field responds to losses in mass stored on the Earth. So this could be ice sheets, but also water stored in reservoirs or extracted via groundwater. So the local projections are derived from the global projections. And on the left-hand side, you can see the various terms that contribute to global sea level. And what we have is effectively a scaling factor, which regionalizes the global projections to a specific location. And the contours you're seeing are the patterns of change for each term. So if you look at the different processes, if you take Diamond Harbour in, I guess, the northwest and Chennai in the south, you can see that the kind of the far left column of these is the total change, and then the others indicate the processes. So you can see that Antarctica dynamics is one of the larger contributions, and also ocean processes, that's circulation. So that's kind of roughly what we're expecting, that the ocean would be, ocean processes, thermal expansion would be the main driver. But if you start to look at differences, so this is the difference between Diamond Harbour and Chennai, you find that actually the contribution for that is quite similar, and we start to see contributions from these smaller terms such as land, water, and GIA. This is more marked for actually the Arabian Sea. So you compare Karachi and Cochin, you can see this small land water term actually is driving the differences between sites. So how does that come about? So these GRD patterns occur where if there's addition of mass to the oceans, so melting ice adds water mass to the oceans, but so does the extraction of groundwater, because that eventually makes its way to the oceans. And because you've changed the distribution of mass, you get a change in the gravitational field. That's the main aspect, but you also get slight changes in the rotational rate because of conservation of angular momentum, i.e. you're moving mass from, say, the poles to the equator, you're changing its effective radii. And also there's deformation of the surface. The groundwater bit maybe is perhaps a little bit hard to understand. So essentially, where you've got lots of water stored on the land, there's more mass there, and that has a gravitational attraction. But if you extract that groundwater, there's less of a gravitational pull, and the surrounding waters flow away. So if you have an area of high groundwater use on a kind of continental scale, you see a near field actually fall in the sea level and a far field rise, and you see something similar for the ice sheets. So the problem is there's a bit of disagreement over whether groundwater will be the dominant process or impoundment. So what the complication for this region is that it's been a region of high groundwater use, but also construction of dams. So this plot on the right is showing the change in sea level, local sea level due to land water storage changes per change in global sea level. So where the blue areas are, there'll actually be a decrease, and the red areas will be an increase. And so you can see that the kind of South Asia region is the center for mass loss from land water storage changes, but this was just with one solution. So historically, impoundment in reservoirs has been the dominant process, so the change would actually be in the reverse. So looking at this map, you'd expect Diamond Harbour to have less sea level change than, say, Chittagong, because it's partially offset by the land water term. But the reverse would hold if instead of groundwater, you had impoundment going forwards. That's one of the uncertainties we've got to contend with. So sources of uncertainty. So what I would need to include is there's new updates for this land water use term that takes into account dams that are under construction or are going to be built. So currently it assumes that groundwater becomes the dominant process in kind of early 21st century, whereas actually more recent work suggests it could be as late as 2040. The other thing is, when you actually look at the observations, it's local processes that are the most important. Things like subsidence can be orders of magnitude higher than the processes contributing to the differences that we're talking about here. So this is some work from Becker et al. With colleagues from Buet. So I guess the summary here is that future changes in the Bay of Bengal is mostly down to changes in ocean circulation and density from heat uptake, but the spatial variations are influenced by land water storage changes. On decadal timescales, sea level variability will be much larger than those. As with global projections, the uncertainty is mostly from the Antarctic ice sheet dynamics contribution, and the upper end of that has increased since the last assessment report. And I guess the final one is that anthropogenic subsidence, which can be caused by, I guess, land use changes and embankments and things, can cause subsidence, and they can be highly localized, much larger than kind of the sea level rate, and also discontinuous in time, so difficult to model. And I think I'll leave it there. So if you want more information, the reports on this work are on the ARC website, and for the kind of underlying science, see the paper Palmer et al. So with that, I'll lead. So thank you for listening. And these are kind of just projections for some numbers, if anyone's interested. So I guess the key thing is that the main uncertainties come from these local processes. And if we're going to make local scale projections, we need to kind of work with people that are expert in modeling kind of things like subsidence and work out a way to incorporate that into the projections.
Okay. Mr. Ben, finished your presentation? Okay, thank you very much. Thank you very much for informative presentation regarding the sea level rise in South Asia. I would like to open the floor now for questioning. If there is anybody, please.
May I ask a question?
Yeah, please. Dr. India Abdul Mannan.
Yeah, thank you, sir, for giving me floor. Actually, I didn't see whole presentation, but I have an interest to know about something from Ben. Dr. Ben, thank you very much. I have, of course, from BMD, we are very much familiar with the UK Met Office. Thanks for your presentation, as well as what I have seen that you have been working with the Bangladesh points like Teknaf, Cox's Bazar, and some other places. We are very much grateful to you. Whatever I found in your last slide in the conclusion, you have been using the CMIP 5 data. So far, my understanding, is it okay? But have you tested for CMIP 6? Because the scenario approach has already been changed.
So thank you for your question. That's a very good point. So for CMIP 6, not all of the variables at the time we started this study were available. So there's two things we need from the climate models, which are the global ocean thermal expansion and also ocean dynamic sea level. And those weren't available when we began this study. And the other aspect of this is that the method's been tested with CMIP 5, but we haven't internally developed the process with CMIP 6. But that is something we're looking to do in the future. And actually, all of the kind of underlying code for this is going to be released as a open source tool when that step's complete. I think that's the plan. But no, it's a very, very good point, because there are important differences actually with CMIP 6 for global thermal expansion that are coming out in the literature.
Okay, thank you. Thank you very much.
Well, I think.
Can I ask one?
Yeah, please, sir.
Thank you, Chair. Benjamin, this Himalaya is very important, and from the glacial melting point of view, being third pole and a house for a large number of glaciers, and with climate change, there are a number of opinions on the contribution of melted water to the oceanic water. What is your take on that component of additional water in addition to the groundwater variability you mentioned? Over.
So that's good. Yeah, that's a very good question. So for the glacier contribution, it's larger than groundwater, but it's similar at all locations, so that when you look at the differences, it doesn't become as important. But in terms of magnitude, it is larger. But actually, the main influence, I suppose, for this region from the Himalayas is on kind of seasonal timescales, because of the fresh water input that you get during the monsoon season. So you see quite large, I guess, seasonal changes in sea level. And an extension of this work, some people at the Institute of Water Modelling want to look at also including kind of seasonal variations in sea level on top of these projections. And that would have to take into account the influence of the Himalayas through kind of runoff. Does that answer your question? Thank you very much.
Ben, may I ask a quick one?
Yes.
On your last slide, you mentioned decadal variability.
Yes. So I can't actually get this up at the moment. Yes. So we were talking about if you take the contributions to uncertainty over the kind of up to 2100, you can work out how much the contribution to the variance is. So in the near term, it comes from the variability that you see in the tide gauges, the year-to-year variability. But the size of those changes relative to the sizes that you see in the changes to the projections become as you get up to the end of the 21st century.
Yeah,
so year to year, you could have like, we're talking, I mean, for something like ENSO, obviously you can have huge changes associated with that.
Is it mainly wind driven? The decadal changes are mainly wind driven?
So there's circulation changes that are tied to wind atmosphere processes, so wind driven. There's also changes in heat in the ocean as well that vary. So from ocean processes, things like for example, there is actually a reduction in sea level during a positive ENSO, for example, in the Bay of Bengal. That those sort of processes contribute to the kind of near term and the decadal variability. But this is it's my colleague Matt Palmer's. That's his kind of area, heat uptake to the ocean. So I'll have to check, but I believe that's right.
Thank you.
Well, thank you. We have some time constraint. That's why we cannot take more questions. Now I would like to request Mr. Himel Bosu for his presentation on his title paper, Climate Change Analysis for Bangladesh using CMIP 5 models. Mr. Himel Bosu, he is from Department of Meteorology, University of Dhaka.
Thank you, sir. Can you see my screen?
Yes, we can see your screen.
Okay. Thank you. I am Himel Bosu, MSc student, the Department of Meteorology, University of Dhaka. My study title is Climate Change Analysis for Bangladesh using CMIP 5 models. My total presentation is divided into 6 parts. These are introduction, study area, data and model, meteorology, results, and conclusion. The first part of my presentation is introduction. So climate change is considered as a major global issue. It poses significant challenges to human existence and socio-economic development. In Bangladesh, so due to lack of detailed study on climate projections and the variability of climate changes, its impact on natural disaster and economy is poorly understood. In this study, an attempt has been taken to build an algorithm for climate projections over Bangladesh under the 5th phase of the coupled model intercomparison project, which is known as CMIP 5. The objectives of this study are to determine and correct the bias of the CMIP 5 GCM model's output through suitable methods, and to analyze the changing behavior of rainfall and temperature over Bangladesh up to 21st century using CMIP 5 models. This figure shows the map of my study area. My study area is total Bangladesh. For the analysis purpose, Bangladesh is divided into 6 parts. These are northwest, northeast, west central, east central, southwest, and southeast. Here in the table, the individual range selectlon for all the areas are shown along with the BMD stations in the region. For example, in the northwestern parts, there are 4 stations of BMD, which are Bogura, Dinajpur, Rangpur, and Sayadpur. For this study, observed data of temperature and rainfall are collected from BMD. The downscale CMIP 5 GCM models data are downloaded from CCCR. CCCR is the regional data portal for Codex South Asia. Data are downloaded for both historical and future simulations. The historical simulations are from 1950 to 2005, and future simulations are from 2006 to 2099. The resolution of the data set is 25 kilometers. Among the 4 RCPs adopted by IPCC, RCP 4.5 and 8.5 are included in this study. Then, on the basis of the same ensemble member, from the models available at Codex for South Asia, first 3 models are selected for this study. All the models runs for the same ensemble member R1, I1, P1. These 3 models are MPISM LR, MPISM MR, and NOR-ESM 1M. Here the first 2 models are German model, and NOR-ESM 1M is Norwegian model. And here R is realization. Realization means initial starting point. I is initialization. Initialization means initial condition. And P is parameterization. Parameterization means it's model physics. So realization, initialization, and model physics are same for all these 3 models. The 4th part of my presentation is methodology. In the analysis of historical period, model averages and trends are compared with observed averages and trends during the same period of 1981 to 2005, as consistent observation is available during this period. For better understanding, the analysis period has been divided into 2 time slices. The period of 1950 to 2005 has been defined as P1, and the period 1981 to 2005 has been defined as P2. Then we will use R programming for bias and RMSE calculation and Python programming for bias correction. This equation 1 is used for bias calculation, and equation 2 is used for RMSE calculation. After bias calculation, we based on this baseline period, which is 1981 to 2005, we bias correct the future period, 2006 to 2099. From the different methods of bias correction, we use the quantile mapping method. This equation 3 is used for bias correction. Here the differences between the observed and simulated CDFs for the retrospective period are quantified and then applied to the future simulations for a given percentile. So basically, this is the process how quantile mapping works. Then the future data of temperature and rainfall is analyzed over 3 distinct time periods with respect to the baseline periods, which are the near future period 2025 to 2049, the mid future period 2050 to 2074, and the far future period 2075 to 2099. The fifth part of my presentation is results. So if we see the historical behavior of rainfall and temperature of Bangladesh, this figure shows the multimodal ensemble variation of monthly average and seasonal average rainfall. Here we can see during the monsoon months, the observation is higher than the model, and overall the model underestimates the observation. Now, if we see the multimodal ensemble variation of monthly and seasonal maximum temperature and minimum temperature, here we can see model and observation is almost similar in most of the cases. The observation is slightly higher, but not much noticeable differences. The second part of results is model performance and bias correction. This table shows the bias and RMSE of the monthly data of the selected models. Here we can see for rainfall, the bias value is around 145 millimeter, and RMSE value is around 145 millimeter, and bias value is around 20 millimeter. And for temperature, the RMSE value is around 1 degree Celsius, and bias value is around 0.5 degree Celsius. So we proceed for bias correction. Now, if we see the results of bias correction, this figure shows the evaluation of bias corrected monthly rainfall. Here, the red spikes are before correction, so green spikes are after correction, and blue spikes are observation. Here we can see the after correction and observation lines are much closer than before correction and observation. So we can say quantile mapping bias correction reduces significant amount of biases from the rainfall data. Now this figure shows the evaluation of bias corrected monthly maximum temperature. Here we also can see the after correction and observation lines are closer than before correction and observation for all the models. So we can say quantile mapping reduces biases from the temperature data also. The last part of result is future projections. So if we see the future changes in rainfall, this figure shows the special distribution of future changes in rainfall in relation to the reference period for 3 future periods, which are near future, mid future, and far future. Here we can see rainfall can change between -20 to +20% for individual models. Here we can see highest amount of increase will be in the northeastern and southeastern parts of Bangladesh, and lowest amount of increase will be in the west central and northwestern parts of Bangladesh for all the models. Now, if we see the multi-model ensemble projected changes in rainfall, we can is under RCP 8.5. Rainfall can change between -3% to 9%, and for RCP 8.5, rainfall can change between -3% to 15%. And amount of it will be in the northeastern parts of Bangladesh under RCP 8.5 in the far future period. Now, if you see the future change in maximum temperature, this figure shows the special distribution of future changes in maximum temperature. Here we can see some between 0 to 5 degrees Celsius. Under RCP 4.5, these changes can be around 2.5 degrees Celsius, and for RCP 8.5, around 5 degrees Celsius. Highest amount of increase will be in the northwest and west central parts of Bangladesh. Now, if we see the multi-model ensemble projected as a maximum temperature and as a minimum temperature, here we can see temperature can change between 0 degrees Celsius to 5 degrees Celsius. 4.5 changes can be around 2 to 2.5 degrees Celsius, and for RCP 8.5, 4.5 degree to 5 degree Celsius. This amount of increase will be in the northwestern parts of Bangladesh under RCP 8.5 in the far future. Now, if I conclude, by the end of the 21st century, the multimodal ensemble annual mean rainfall average to Bangladesh is projected to change between -2% 4.5 and -3% to 15% under RCP 8.5. Annual mean maximum temperature is projected to increase by 1.9 degrees Celsius under RCP 4.5 and 4 degrees Celsius under RCP 8.5. Annual mean temperature is projected to increase 2.1 degrees Celsius under RCP 4.5 and 4 degrees Celsius under RCP 8.5. And finally, the northern part of Bangladesh is highly vulnerable to climate change due to the large increase in the projected annual. I would like to acknowledge Bangladesh Meteorological Department, Dhaka, Bangladesh, for providing me the necessary meteorological data as received as guidance. Thank you all for your kind attention.
Thank you very much, Mr. Himel Bosu, for presenting for very important information us, and it is alarming to the Bangladesh professionals and scientists that you are predicting that 4 degree temperature, 4 degrees Celsius temperature will rise in this century to 2100.
Thank you, sir.
Also, you are projecting rainfall increase 9% to more than that. That is probably -3% to 9% probably in your RCP 4.5 pathway projection. So this is very much alarming. And now I would like to request the audience for questioning Mr. Himel Bosu, please.
Sir, thank you, sir. May I ask a question, please?
Sure. Dr. Mohan Kumar.
Yes, sir. Thank you. Actually, Himel did a good work, good research work in a very limited resource. So, I asked Himel, why you only consider the mid-level and extreme level scenario? Why you not consider 2.6 or nearest scenario? One small query for you. And I would...
Actually,
yeah.
Actually, RCP 2.6 needs high mitigation measures, and considering the current situation, it's not possible to maintain high adaptation measures. So that's why I don't include RCP 2.6 in my study. And RCP 4.5 and RCP 6 both are medium stabilization scenarios. So if I take RCP 4.5, then I can cover RCP 4.5, RCP 6, and RCP 8.5. That's why I choose RCP 4.5 and RCP 8.5 for my study.
Okay, good. And just you take one more initiative to publish your study in a very good journal. Thank you, Himel. Thank you for your good work.
Yes, sir. Thank you, sir.
Can I ask a question?
Yeah, please.
Yeah, thank you. Very nice presentation. But my question is, why do you like choice only 3 model? Because you can use a lot of model. You can also use the ensemble a lot of model. I think you can get more better result. So.
Actually, sir, it's a part of my MSc thesis, and I show the individual analysis of all the models. I take 3 models, and I have shown individual analysis of all the 3 models. If I show it's only multi-model ensemble, then I can take more than 20 or 30 models. But as I have analyzed all the 3 models individually, so it's not possible for me to take more than 3 models within this short time.
Okay, thank you.
But in future I will work with the CMIP 6, and there I have I want to take only it's a multi-model ensemble including more models.
Good, thank you.
Thank you, sir.
I have one question.
Yeah, please.
Among the 3 models, which model performance is best?
Among the three models in my study, MPISM MR, the model is best model for projection over Bangladesh, because the bias value and those RMSE value is also lower for this model.
Okay, thank you.
Thank you, sir.
Is there any question? I think there is no question. We have another 10 minutes to conclude this session. Before handovering the floor to our chair, honorable chair, I would like to just mention something as a conclusion speech. That there were 5 speakers and they have given some good information. First of all, Dr. David Faria, he has given information regarding the that is circulation of use of warmer climate and MSC as well as NEI increasing. Thanks to Professor Dr. David Faria for presenting very important information of meteorological through his nice information. I think this information will be helpful to the scientists for updating climate model for future climate projection. Next speaker, Mr. Muhammad Tanjilur Rahman. He also has given some good information regarding the seasonal rainfall increasing pattern in all the season in Bangladesh. So that will be also helpful for the agricultural profession for rescheduling of the cropping pattern and cropping calendar. Also, it will be very much informative for the flood and drought risk management in Bangladesh. Our third speaker, Dr. A.R. Tawfiqul Islam, he is associate professor from Begum Rokeya University. He has also given some information regarding the temperature increasing on the basis of our global warming, and he has given information on towards our northwest and western part of Bangladesh, where we are facing actually less rainfall during even post monsoon. So this information will be also helpful for the Bangladesh professional Bangladesh government, for the policymaker, for taking care of their future plan. And fourth speaker, Dr. Benjamin, he has given a sea level rise projection, new sets of sea level rise projection in the southeastern region, different tidal stations, and he has found that the regional this sea level rise is lower in our South Asian point, especially Arabian Sea as well as Bay of Bengal, and he is trying to explore the driver why this sea level rise is lower than in comparison with other area in the world. So that will be also good information for us, because we are facing sea level rise in Bangladesh, and through which we are getting high altitude of storm surge during the cyclone. And the last speaker, Mr. Himel Bosu, he has given very good projection, good research presentation regarding climate change analysis of Bangladesh using different models. And he has also shown some variability of rainfall and temperature increase, and very much alarming message from his research, which is required for our government and policymakers as well as professionals, those who are working in this meteorology related disaster like flood, drought, this kind of management. So thank you very much for this nice presentation, and I also thankful to, once again I want to tell to that I'm very much thankful to Professor Tawhid Rashid, Chairman Department of Meteorology, and his team, Javed, Shubho, for arranging this session and inviting me as a co-chair. And also I also thankful to our chair, Dr. L.S. Lathur, for giving his valuable time for this session. Thank you very much. Thank you, everybody.
Thank you, Dr. Mijanur Bhai, and I think we had a very interesting session, and the title was itself very interesting: climate change and future climate projections. There is a global concern on the future climates, and a lot of efforts are being exercised to respond to likely changes. Not only likely changes, we are in the current era also are facing a lot of challenges in developing climate information-based services. For larger part of my career, I was confined to the weather aspects and the services which are based on the weather information. And now things with the better climate information seems to be really changing, and we are juxtaposed at such a level that we are able to deliver a good service, especially in sector like agriculture, water, health, and also disaster risk reduction. And to that direction, the today's session is really very important. And we had, as co-chair mentioned, very interesting presentations, though there are only 5 presentations, but they were really a good sample of the entire gamut of the climate change aspects. The David made a very good presentation on the energy aspects, energy budget of the tropical band, and how that is linked to the future climates, and really gave a good insight into the GMP, GMS, and the both, because energy is directly linked to the moisture flux, and moisture flux is directly linked to instability and the height at which convection can really take place. So that gave a good insight into energetics of likely climate changes. And the Tanzilur also downscale rainfall projections, and while doing dynamic downscaling, we got some handle on as to how the flow pattern might be influencing or might be influenced, ultimately leading to the rainfall behavior over Bangladesh. So a very good study. And the study by Taufikul also on the vegetation change, because the climate change, we definitely need to assess as to how the food security is going to be impacted because of the climate change. And to that extent, this study was also equally important. And so also the sea level, and how the sea level is linked to the ground level, as was researched by Benjamin Harrison. Very interesting study. And the last one given by the Himel Posu, where he used SEMI-5 models for Bangladesh to really understand the dynamics of climate change analysis, etc. So give a very kaleidoscopic overview of the good components of the future climates regionally, as well as for the country's specific aspects related to the future climate projections. So many thanks to all the speakers, thanks to all the audience which is present and participate actively. And one thing which I really noticed, the Department of Meteorology at Dhaka University, under able leadership of Tawhida Rashid and the faculty, they had developed a good bridge with other stakeholders, and particularly the Bangladesh Meteorological Department is giving a good handholding. And I can see that some of the data flow from BMD to the Department of Meteorology, which is a positive sign, and also the outreach with University of Reading and the UK Met Office, that really underlines as to how the department is actively trying to address the problems of country, problems of the region, and the global issues related to weather, climate, water, agriculture, etc., etc. So my compliments to all the organizers and Sama and all the friends, and nice to meet all of you at this forum. And so on behalf of my co-chair and myself, I thank all the organizers for giving us opportunity to chair this very important technical session 7 and share some of our ideas. Thank you very much. Goodbye. Over.
On behalf of the organizing committee and Department of Meteorology, I would like to thank Honorable Chair and Co-Chair for conducting the session and all the presenters for their wonderful presentation. I would like to thank all the audience for being present in this session. The next session of the conference will be start at 17 in Bangladesh Standard Time. So all are invited to join the session. Thank you all.